small series on research and practice. And as a last lecture, I'm delighted to have to introduce Ahlquist tonight. Knowing his work to a degree, it also nicely sums up that which is the topic, research and practice, by, I don't think I would exaggerate by saying putting the emphasis on research. Moreover, it's also rounding off then the series and opening the door to what would be the absolutely last lecture in this academic year. It is the Dean's Honorary Lecture during our end of year review in July. And on Thursday, the 7th of July, Sanford Quinter, who's a professor at Harvard, will be giving this lecture, which we call the Dean's Honorary Lecture. And it is precisely of interest because what Sanford has been, not masterminding, but what he certainly has contributed an enormous amount of ideas to over the last 10, 15 years, is trying to rethink architecture through a certain type of materialism. It's a certain type of materialism that I would certainly sign up for in the sense that it radically transforms how we think about design. It radically transforms the way that we can go about both thinking and practicing architecture. It has to do with considering materials rather as a medium through which information flows. It has to do with considering materials as just one, as a very subcategory of something much vaster, which we would generically refer to in English as matter, a sort of generic realm from which we draw all types of materiality. And the essence of architecture in relation to this is precisely design. Design thinking, design practice, design as a body of intelligence. And I say this with respect to that lecture in July because I think that right at the moment there are very few people in the world who's actually doing practical work that may contribute to the same. It may not be as have come as far in making substantial claims to paradigm shifts as that which Sanford outlines in some of his writing and thinking. But Sean, together with colleagues in Stuttgart right now, and previously also, I think, in the better days of the Emerging Technologies program at the AA, where Sean took his master's degree in 2009, have, to various degrees, contributed to shifting the attention to how we go about thinking about materials and material systems in architecture. Sean refers to his own work in terms of biomimetic thinking, physics, biology. So it draws this way of approaching architecture through the material paradigm, draws on a wide spectrum of various contemporary sort of findings in different fields. But it is also fundamental in, I believe, rethinking certain things that took place some 13, 14 years ago. I think, of course, not far down from the institute in Stuttgart, where Fly Otto was based, and which is a central reference for Sean and others. I believe it's a rethinking of also that work and those findings in the manner that it shifts basically a logic of form finding to that of form generation. Where I get most excited, and this is the privilege that I've had with Sean, but also with Sean's colleague Achim in Stuttgart, is of course to speculate on this in relationship to architectural design. Because as a body of research that is devoted to material systems, to certain systematic ways of setting up how to design sub-components that go into the large complex of what architecture is, I believe, I'm not getting too many words right now, but I believe also there's a gradual shift in your way of approaching this work, where it moves gradually towards architecture in terms of the spatial paradigm, in terms of the spatial discourse. So, I am very excited. I've had the privilege of getting to know the work by and by over the years. I've up on the very many publications. There's a forthcoming book on computational design thinking that Sean is working on. We have edited Achim. So Sean is very active in terms of the research for his PhD as much as in terms of presenting papers and publishing. And it only remains for me to say that also I am looking forward to more detailed and more intimate sort of understanding of that work tonight.
Thank you very much for having me down and very well-spoken introduction. And I think maybe if I can pick up on at least one of the terms out of that I think we'll kind of go through a few of them, is this idea of sort of design thinking. And I'd say one of the kind of stages of evolution that we're in the moment is that we're kind of moving away from considering design as a critique of technique, and design is really is a critique of design. Technique being intimately connected with that, but not the sort of core criticism. And what that means is that, all of these considerations, the result of the process, the construction of the process, the information which is built into the process, these are all kind of inextricable items. And this is sort of, I think, one of the critical points that I'm trying to make with my research. But at the same time, of course, be able to frame that within the idea of sort of design thinking, not just kind of practice and process. So I'll start with kind of this quote, which I think, again, kind of reflects this sort of frame of thought in terms of how you might want to deal with architecture. So this was posed by Nicholas Negroponte in the 60s when computation sort of first started to appear in architecture, or was first introduced to architecture. And this was the kind of critique of the architect's approach. There's of course large-scale problems to deal with, but they're sort of too large and too complex to be able to resolve. And then of course there's the small details which at the same time are complex, but then again also maybe too banal to consider in the process of design. So unfortunately, if you think about it, I mean, what that means is you sort of, have to oversimplify on one level and you have to disregard on the other level, and you fall in this kind of middle ground of being the sort of ultimate generalist. Everything becomes a generalized idea or concept or even data. Or you could even think that in some cases, to accomplish maybe the consideration of detail, you have to sort of neglect things on the other scale. So ultimately, the idea is, can we actually address both levels of the system, both scales of the system in terms of design process, but also in terms of the operation of architectural systems. So it kind of brings up, and I'll just go through this very briefly, it sort of brings up this question in terms of what we call computerization versus computation. So computerization being sort of the automation of what might have been traditionally manual processes, and the idea that the collection of knowledge is sort of a reiteration of pre-existing knowledge, sort of a reorganization in very linear processes. Whereas the idea with computation is that it's actually an information forming process. So what starts with very simple basic principles and sets of ideas, through iterative means and measures, can actually evolve into what should become very specific and operational systems. And I think this image kind of addresses sort of the struggle of how to do that in terms of looking at it as an architectural system, the idea that elements operate independently, both physically, but also in terms of their functionality. So it's sort of an accumulation of independently hierarchical layers, as opposed to an integration of hierarchical systems. So there's certainly, kind of precedence to think about the relation of systems in design, shaping systems in terms of rules and how these work parametrically, of course. In this case, the design for, a loading bay area in the Sydney Concert Hall by Jorn Utzon. So the idea that the process is actually about stating steps of transformation, in this case just the geometry, of course possibly having to do with the structure as well, but the idea that there's an understanding of the systematic nature of developing form. And then introduced by Christopher Alexander around the same time again as computation was introduced to architecture in the 60s. The idea of how systems can be translated in different ways. So depending on the information that you have, how can you actually understand and construct the system? So we try to look at in terms of how we can define that system, how we can define an architectural system through this process of computation as opposed to computerization. It's actually this study of kind of multiple concepts, multiple sets of information, and multiple kind of fields of study, let's say. And the integration of these is sort of what culminates into computational design. So first I want to take just kind of a quick sort of reference to the idea of understanding natural systems, which in one sense, of course, can have kind of formal ramifications in terms of, materiality and structure and function and operation, but also in the other sense, understanding how processes of materialization have a relationship to performance. So in the case of, just looking very simply at the fly, the standard fruit fly, these, of course, existed for many millions of years, and of course they used to exist as extremely large insects, much larger than what they were before. And the reason is they existed in a very oxygen-rich environment. So what's interesting is the genetics have not changed with this insect. It's merely the same kind of actions occurring, but the responsiveness to the amount of oxygen in the environment is what constrains essentially this growth system of the respiratory system, of the kind of respiratory framework for the insect. So it has this kind of branching morphology which has a key kind of relationship to the environment and constrains its growth based on the amount of oxygen that it can absorb. So there isn't, a kind of button or a single trigger which is telling it to grow to a certain size or another. It actually doesn't know what size it's going to grow to until it actually interacts with its environment. So I think that in terms of understanding process, in terms of understanding internal logics, internal material logics, and how those internal material logics are influenced by external conditions to create a kind of performative system. So if we look kind of quickly how, we might start to understand that in terms of even just a geometric way, looking at the concept of a minimal path, a very simple geometric rule, and has certainly been studied before, in this case, work by Frey Otto. But I think that the challenge in relating our work to extracting these ideas, is this going to play for me? It's trying to play. Okay. Oh, maybe not. Okay. Unfortunately, this was sort of a form-finding technique with springs for realizing a minimal path arrangement. But nonetheless, the idea is that with this kind of rule, of course, you can devise. There we go. You can devise the geometry. But the problem is it's just based on a single set of rules. So there are no other conditions, there are no external influences, there isn't anything else which is affecting the arrangement of this geometry. And ultimately, that is kind of the primary condition that we have to consider in terms of a system. A system isn't just one single set of operations. A system can't operate in that way. It actually has to work at multiple levels to find its kind of equilibrium state. So the question is, now when we start to consider these kind of multiple levels of operation, sort of these interaction of what we might call behaviors, the question is, how do we actually start to compute that? So, the elasticity, the bending elasticity of an object when it's loaded with a certain weight. So again, there's a certain system within the material element, and then of course there's another system of gravity and mass, which is being applied to that, and that's realizing the kind of resulting form of the element. And of resulting geometry. The same in terms of just tension, looking at springs and weights and so on. And then, of course, looking outside of just the kind of structural condition that, there are also kind of other sort of atmospheric, spatial, climatic, material conditions that can be studied as well. In this case, the understanding of radiation, thermal radiation between surfaces. So the question, I think, and in terms of, again, sort of, hopefully throughout this presentation, I'm trying to show sort of the evolution of the ideas as well as sort of the evolution of a application of the ideas. So I think the first step is understanding this relationship between geometry and function, and in terms of function, thinking of this in more the computational realm, a computational function, a computational process, not function in terms of an achieved or a desired goal in terms of performance. That's quite a different application to it. So first I'm going to look at actually a few projects which I did prior to my master's studies in London at the AA. And these actually kind of focus on this idea of sort of visualizing, or in a way sort of hypothesizing performance out of a geometric construct. So in this case, looking at what might be a structural system in relation to subdivision and curvature of a surface, and how you might understand that system as a certain kind of network pattern, radial, distributed, local, so on and so forth. And that the system might exist at again, kind of interacting, but also hierarchical layers, that it can sort of within two overlapping geometries, recede or protrude or so on and so forth. And then, again, kind of, let's say, hypothesizing what actually sort of these layers of geometries mean in terms of performance. So in the case of this project, the study is to create this, what you might call sort of an aqueous skin. A skin which can, of course, hold structure and has a certain kind of subdivision related to that, but also allows for water to be absorbed through the surface into a series of kind of pathways and channels, to which then it's filtered and then it's distributed back through the different kind of services of the structure. In this case, it's meant to be a house. And kind of the resulting level of sort of differentiation that can be gained by varying that kind of, let's say, pattern system in this case. Okay, so moving to another project where this one was actually less hypothetical, was actually a built project. The idea that possibly material might start to have some kind of influence onto the design. So in this case, it's the existing site is on the left, or the pre-existing site. It's not there anymore. And what they wanted was they were building a new building which was going to come to the complete extent of that site, but then they wanted to actually design a skin which could still give the same kind of texture of surface, but also the same kind of privacy of what this kind of thick green layer provided. And this is in Tokyo, where this kind of green layer is extremely rare. So this is the design of the building, and then the thin red line is the area that we had to kind of create that sort of buffer zone. So again, kind of looking at a sort of differentiated pattern, that pattern can be filled with sort of a cellular system, a component system, and then that component system can be accumulated to define a very kind of, let's say, algorithmically rigorous but visually dynamic pattern. And then the result being these kind of layered skins in front of the building. So again, I think so now the idea is, that's sort of, let's say, one method of design, and arguably I'd say it's maybe a bit more focused on the capability of the technique than it is really the knowledge and the results from the technique. But the question I think it brings up is this idea of working with a component or working with a cell. A component, I think by definition, is an element to which its interaction with other elements limits the influence to which that element will change. So a component is something that is very isolated, its rules are isolated, and the influence of its neighbors are extremely minimal, and it usually acts in a very clear hierarchical nature. A cell, of course, is something to which it's essentially a process in itself. And that process in itself is something which absorbs external conditions, so it reads what's happening with its neighbors, and it takes that as input to actually define a reaction to that. So when we go back in that light and kind of look at these sort of component systems, the idea here is, of course, there's some sort of process in terms of how the component is defined. In this case, there's a particular consideration of this kind of webbing, the weight and thickness of the webbing of the system, which is just sort of intuitively defined from an aesthetic point of view, how thick it should be, but also somewhat a kind of consideration of the material, which is a very thin kind of aluminum veneer material. So, of course, changing that process so that you can, gain a certain, in this case, kind of increased thickness in one area, but kind of maintain a very sort of filigree condition in another area. But the idea is, again, because each component works in an isolated manner, it doesn't work collectively. There's really no built-in logic for the panelization system, which is on your top left there. So it's broken down into a grid, and doesn't necessarily have a rule to consider how this kind of attachment system works with this facade. So actually, as a side story, we manually placed every single one of these brackets, and there's probably about 12,000 of them that line the entire system. So. So again, that's why I think it's very clear to consider that as a component. It's something to which the external rules of what happens across the entire system has nothing to do with what's actually happening locally. Nor does this even is there kind of this consideration in terms of the cell, this idea of, ultimately what is one of the performance considerations of what happens in the end, this kind of ability to sort of out of two static layers create a kinetic facade. So of course as you move by this sort of patterns of openings and solids and voids is what changes, but that's a resultant effect, but not something that's really considered or controlled in terms of what happens with the cell. So then kind of, again, looking back at the second project, the jellyfish house, really thinking that it is just a hypothetical in terms of performance, to imagine that you have sort of pathways of water, charging the system to move it through, to filter it, and so on and so forth. I mean, honestly, it's quite a reach to think that you can pressurize a system of that scale. But even yet again, looking at the technique, which in this case the technique was something that was at this time actually, arguably a bit fairly inventive in terms of the complexity that could achieve. The geometry, the technique, the pattern, it has nothing to do with the relationship of how it would actually perform as this kind of water filtration and distribution system. So, it's just kind of pointing and saying, there's the channel where the water goes and there's the channel where the filtration happens, So there's very little kind of literalness other than the visual and formal nature of the geometry to the actual performance of the system. And I think dealing with behavior, of course, you can't work in that fashion. So referring back to Sanford and his idea of material and matter, I think is kind of stated clearly already and very nicely by Johan. This idea that there are pressures of all scales, which are the things that define form. I think that's something that has to be taken seriously in the way that the processes work, and of course in the way that you kind of approach architecture, the way that you think of the performance of architecture. So if we kind of refer back to that first statement, I think what Nicholas Negroponte is referring to very clearly is this idea, that essentially you have to think of architecture as a system and really as sort of layers of systems, but that you also have to stratify it in terms of the systems which operate on the level of architecture and also the systems which work as the generator on the level of design, because these actually are two kind of synchronous design aspects, let's say, but they also can function quite differently. The generating system, of course, is to a certain degree about simulating the operating system, but it doesn't really function in the exact same manner in that sense. So when we look at system, the idea is to establish what are the ways in which you construct a system. Of course, we've heard the idea of systems architecture, for ages, but I think again it's more of a hypothetical application to the result of a non-relevant technique, and it's really just more of a kind of wallpapering on top of a sort of complex result, let's say geometric result. So when we look at systems, Ludwig von Bertalanffy was one of the first people to establish this kind of general systems theory. And first he's kind of, to put it very simply, looks at two different levels. First, the idea of a feedback system, understanding that a system is always trying to accomplish an equilibrium or a homeostasis. So there's always, of course, it's operating to find a certain kind of balance. And for that balance to be found, it has to be an iterative process. It has to be something which provides feedback to reinform the system and to build the degree and sharpness and accuracy of the information. So then when we start to break it down, there are sort of three aspects which you can look at to be able to achieve that. One is the count, the number of elements in the system. Two is the type, what type of elements in the system are there, how many different types are there. And then the third is association. So that's kind of the three different levels described there. And of course, most critically is this definition of the association. And when we look at John Holland's description of a system, we understand that this idea of association is more about not just kind of the literal connection of elements, but actually how these connections might change, or how the performance of the system would change as a whole from the transference from one state to another. And the idea that this is captured as an algorithm, it's captured as a process to understand this transformation, what John Holland calls as a transition function. So the idea, okay, we have some idea about how to construct a system, how to understand the different, maybe define the different elements of the system. So now it's a question of how do we actually build knowledge? How do we build this into an architectural system, an architectural generating system in service of architectural operational systems? So there's the kind of two sort of frameworks that you can look at. One is understood as a kind of knowledge-based design, to which this sort of maze is an analogy for the idea that the entire set of information is there, and it's more of a problem-solving issue in terms of testing the different options, testing the different pathways to which you can reach your goal state. And of course, in this case, the goal state is very clearly defined. If you're working in a knowledge-based method, it's typically based upon precedence. So of course, to establish your precedence, you know what the result has to be in terms of performance. If we look at something which is can be called, it's hard to find case conditions which can apply broadly in a more broader context. But with the idea of abduction, which is an application of the development of prototypes, you can sample from existing conditions to set up, or I think more importantly actually, sample from existing processes which can set up new examples of cases to be studied and developed in the kind of process of iteration and formation of the design. So the idea is not looking at kind of the one result, but actually looking at the process and taking the process as a prototype, in this case an L system, the process is a prototype which can be executed and developed in purpose of a new context and set of performances or functions. So I think in that context, I think this is a really kind of important phrase to understand, that behavior is this kind of link between function, which you could understand in sort of a knowledge-based context, and form in terms of more, in terms of a systems approach, that form is not actually the kind of simple static material result, but it's actually the kind of operation of that material and the operation of the environment and function and program which exists in and around those material forms. So again, kind of understanding behavior on another level, the idea that behavior is actually more of a transition function. It is a series of operations in itself which captures other behaviors. And the idea that how we can move away from this sort of idea of knowledge in terms of special purposed packaged processes as defined here, but knowledge maybe in terms of the formation of a meta process to which specification can occur in the development of design and not be a pre-existing issue. So of course, interestingly enough, and sort of a point to this, this is a quote from 1975, which is a bit of a kind of reaction after the first wave of computation to make some presence in architecture. Actually had all these ideas back then, but somehow, it really kind of changed track from specialization and customization into standardization in terms of course, the kinds of parts and pieces to which we use in architecture, but also the kind of processes and elements which are utilized to develop the designs for architecture. So looking at the idea of action, and I'll kind of go through this project a bit quickly, but The idea here is to actually try and understand this term of system in terms of geometry, in a sense as an action as opposed to an action which can absorb kind of external contextual conditions as a way to generate form. So in this case, the action is a very simple rule, understanding a given volume, how you subdivide that volume, and how you can iteratively subdivide that volume to distribute a certain kind of spatial or organizational kind of pattern, which is what we see on the kind of top right. The sort of vertical bar is a particular kind of organizational data set which is trying to be distributed throughout a given envelope. So in this case, distributing these three types of organization within a certain envelope, and the subdivision algorithm works to iterate successively until it distributes all of those bits and pieces of organization into the overall form. So looking at an example, in this case kind of taking a high-rise building where the distribution of organization actually considers both the kind of use of space as well as the void space, which is the second one from the bottom here. So that's sort of an active participant in defining the distribution of space. It's not sort of a negative or leftover condition. And then, of course, it runs as an algorithm, as a process. So, looking at the multiple iterations, the question is, of course, as it is a process and not a specific kind of formal algorithm, you have to, of course, analyze it via other means to try and understand the system. So analyzing the different kinds of distribution and how they might rank in terms of each other. And of course, looking at performance on different scales in terms of shading and thermal exposure. Then, the system is able to kind of study a particularly kind of constrained distribution of organization, but through, multiple kind of highly differentiated formal results. So the question was really at the end of this, like, it worked as kind of in this method of developing an algorithm which was based on a process as opposed to a kind of specific or constrained or isolated geometric algorithm. But really we didn't know what to do with it beyond that. So, does it also have kind of a material sort of condition to it? So that was sort of the kind of ending point of that process. So now we start to look at, which this kind of really falls into the crux of my research, is this ability to consider morphology as a kind of inextricable relationship between, in this case, the level that we're at the moment, this inextricable relationship between what is form, the structural condition of that form, how is it realized as a stable structured state, and then how is that state materialized. So what we look at is what are called tensile structures, which if you're in southern Germany and anywhere near Stuttgart or Munich, you understand through Frey-Otto's work the idea of tension active structures. So where a tension force is used to essentially structure a surface so that every element is in pure tension and creates a stable condition which can withstand other external forces such as gravity, wind, and other loading. So examples in nature, of course, of spider webs, and then of course in architecture in terms of cable nets as well as membrane architecture. The specific kind of avenue which we're looking at is what we call sort of a deep surface system, which actually integrates both of these kind of structural strategies. So two layers of a tension mesh, so an open web mesh, and then occupying that with a sort of surface structure which spans between it, and again that the entire system is structured and stabilized by the application of tension forces to the boundary conditions. And there is precedence in this in architecture. This actually is again back at the Munich Olympic Stadiums by Frey-Otto. This is in particular the swimming hall There are what are called these kind of multi-layered membranes, which in this case we have the tension cable net surface above, and then we have a tension membrane surface below. And here it's used as a kind of insulating layer for the swimming area below. But really the consideration is how to integrate, how to define form via these kind of multiple parameters, which again are sort of inextricable to understanding the system. If you erase any one of these steps, then the result is really just has nothing to do with material, and it has nothing to do with this kind of literalness, which I referred to before, in terms of the result and in terms of performance. So the question is, you know, if we build out of sort of points and lines as the most basic functions, you know, what are the ways in which we can actually build? So referring to the first projects, it was more of a kind of mathematical condition. Of course, we can, you know, construct a circle via sine and cosine, you know, very clear. Or we can actually operate by adding additional information to these, or additional potentials to these basic elements of geometry. So in this case here, on the right, sorry, stop that one. This one to go. There we go, okay. So on the left is the calculation of the sine and cosine, you know, very clearly stated. Of course, you know, I was going to draw a circle. On the right is a completely form-found geometry where the center element is essentially a magnet which is repelling all of the outer elements, and then a spring is used to sort of capture those elements back into a continuous circle. So because of the equilibrium of forces between the springs and the equilibrium of forces between the inner magnet, which is pushing out all the other nodes, all the other particles, then we can obviously discover exactly the same form. But the critical thing is really in the next step, to when we start to look at more complicated arrangements. When we're operating on the level of forces and elements in topology, you start to realize that the manipulation in topology has a manipulation of form, and we're at this moment where it's inextricable between the definition of geometry, the definition of force, and the definition of a resulting form. And in fact, probably really geometry is kind of the inappropriate word. Geometry becomes replaced by the definition of topology. So how the elements are connected together and the definition of each element. And of course, as the element relates to its neighbor, it doesn't know what to do until it knows what its neighbors are starting to do. So of course, a spring is not going to do anything until it's actually acted upon. So we start to get this kind of dynamic relationship. We start to have this opportunity to model within these dynamic relationships. And again, there's sort of an idea that this is a generative system which produces a certain system performance in the result. In this case, finding an equilibrium where all these kind of forces are resolving themselves. So just looking at an example of how this might be materialized. This was an earlier study during my master's thesis. So in this case, not looking at this kind of force of magnetism, but just looking at this force of springs, how the springs, again, through several kind of iterative equalizing steps, finds an equilibrium state, and then that resulting geometry, that resulting information of force can be materialized into structure. And then from that, it of course can be parameterized, and now we have sort of a process again which kind of links this idea of material structure and form and tests different kinds of iterations to it. So to kind of break that down a bit and then actually sort of work towards the end with some much more complicated, much more complex form systems. There's really sort of three key aspects to consider, and again, the interesting thing is somewhat that geometry has nothing to do with any of them. Topology is the first one. So again, when you're thinking of how forces are connected to each other, elements which apply a force, how they're connected to each other, then of course the topology of those forces is extremely important, because a change in topology will mean a change in force, which will mean a change in form at the end. So of course then there's the step of how can you actually elaborate upon that force, how can you visualize that force, and then the result is how can you transfer that into a material logic, how is the material logic embedded in these other steps, but what is the final kind of translational step to realize it as a material structure, a tension structural material system. So one thing you have to look at, which is actually super critical right at the start, is with tension-active structures, there's really two very different kinds of systems, and they have absolutely everything to do with the construction of the material. So on the left is of course the kind of warp and weft definition of a textile, of which there are no fixed nodes. So what that means is because there's no fixed nodes, that means an entire sheet of material, the force is always going to try and equalize itself. There is no localized control of force. It will always try to distribute essentially from boundary to boundary, edge to edge across the entire surface. With a mesh, where there are fixed nodes, then the force is resolving itself at the local level, at each local node. So in that case, you actually can accomplish different degrees of tension, different degrees of force, different characteristics of force within that kind of structure. You can isolate areas of higher force and isolate areas of lower force because it's not equalizing itself because of the fixed nature of each node. So what that means is we're kind of up front, we're sort of constrained in terms of how we should visualize the kind of surface, tension surface material nature. And that's done in this case with just a simple kind of quad construction of springs, of spring elements. But on the right, when you're dealing with the fixed nodes, you essentially have kind of ultimate freedom in terms of what the topology is, based upon other rules, which I'll talk about in a second. The main other rule has to do with curvature, so there's a bit of kind of an understanding of geometry. The idea with a stable structure is that you want to not necessarily maximize, but always have a certain degree of equal and opposite double curvature. That's what allows the surface to be stable in reacting to other external loads. And now again, it's not necessarily about actually maximizing that form. In this case, it's actually showing there is sort of a kind of sweet spot, let's say, in terms of the degree of curvature in relation to how stable the structure is. The less curvature that you have means the more force that is necessary to pull on it. The straighter it is actually means there's more force necessary to make it stable. So you don't want to stay to that end of the scale. And then, of course, the more curvature that you get, you're just getting to a point where it's really not efficient with the material. So looking at an example of how to actually study and materialize this, the idea that how we can start to assemble and accumulate sort of multiply the level of complexity and interaction and integration in the topology. This particular system, of course, we have to, again, kind of simultaneously look at the form, the curvature, understand the degree of forces in the surface. So the sort of color visualization from the springs is telling us the sort of degree of equilibrium that these particular geometries have fallen into. And then as in a computational way, this structure, though completely continuous, the force is running from boundary to boundary all the way through the entire system. It's actually really just accumulation of multiple cylindrical topologies. So each colored element is just a cylindrical topology, albeit connected in a different way to its neighboring elements to create a differentiated kind of continuous nature through the whole system. So of course it's maybe a bit obvious in the previous one, but looking at the earlier study of the kind of tension mesh, the idea here is, again, this geometry is formed out of just 3 interconnected cylinders, but again, how they're connected, you can accomplish quite complex geometries. This then also becomes a logic for how it can be materialized. So the 3 different cylinders computationally are materialized as 3 different cylinders and then interconnected in the same way and tensioned, and you have the result. So looking back at this particular project, it's not a mesh, it's not a tension mesh, but actually a tension surface. So then there is yet another level to the logic of which defining the panelization of the system. So how the geometry is separated into individual panels. And then, of course, the trick here is the panelization of the system is not a one-to-one process, because you're looking at it as a tensioned structure. So therefore, you have to sort of de-stress, unstress the piece, so that when it's stressed again, it sort of realizes, it elongates back into its state that's defined with the geometry. So the material kind of translation step very much has to do with how much the material stresses and how much force is in the system. So to get to this final step on the right, you can't avoid any of these conditions out of, having to do with what material it is and having to do with the distribution of forces. So that's what's kind of, all of that is sort of included inside of the design environment, in this case, something which is kind of programmed from ground up inside of processing. And just to give you kind of a quick look, so this is that same system. Of course, again, trying to find that kind of equilibrium, and then being able to, let's see if I can edit this quickly. Being able to look at, how you might start to manipulate certain aspects of that system and kind of change the resulting geometry. Is maybe a bit hard to see that. But the idea is that the kind of manipulation actually has to do with the material constraints, but then still always gives us a kind of equilibrium tensile state in the end, and all the information that we need to extract that back to a material construction. Okay, so 2 examples, or just 2 screenshots from that environment. Whoops, let's get rid of that. Okay, here we go. Okay, whoops, too soon. So here you can see, in this case, the topology is broken down into a series of panels which reconstruct the cylinders and then construct themselves back into the whole system. So again, the kind of material nature has to be built into the modeling process to actually get you back to this resulting state. So in this next project, the idea is that kind of basic component is maybe something more elaborate. Instead of kind of this single cylinder, it's actually one that turns back on itself. But still has to deal with the same issues of how you return that to materialization. So in this case, the cutting of the panels on a cut plotter, and then stitching those panels together, which is actually a pretty exhaustive process. But again, actually an extremely important process to consider, of course, because when you stitch 2 elements together, when you have 2 boundary elements overlapping, you have a different material condition than what you have along the surface. So how you stitch that and how that stitch is made so that it affects the tensioning in a somewhat continuous way as what's happening in the rest of the surface is sort of vitally important. So we get this as the kind of result to that entire thing of making the elements and stitching them together. So essentially this is sort of the realization of 1, the topology, and 2, the understanding of the material. And then, of course, you add the 3rd element, which is reinvesting the tension into the system, and you get the geometry back, and you get the resulting system. So then the kind of last question is, how to what degree can we actually push sort of the complexity? Now that we have a kind of basic understanding for how to integrate the force, how to understand the material behavior within these force diagrams, and then how to translate that computational material behavior back to physical material behavior. So this project, I think, sort of exemplifies a bit more of the thinking as well as the execution in how you can transfer through these sort of steps of knowledge in terms of process and physical prototypes to a kind of operating system at the end. So the first set of studies, it begins with, again, these kind of simple aggregations, cumulations of cylindrical elements connected to each other. The individual element is studied on a more complex kind of geometric level. In this case, it's actually a toroidal topology, so two cylinders connected on both ends creates a continuous toroidal surface. And then, of course, calibrating the computational simulation to actually relate it back to the resulting geometry. And then through that, can start to look at more advanced systems. So the individual component, which you can maybe start to identify there a bit. I think this has maybe 9 components, something like that. The individual component is actually exactly the same topology as this element, though when it's connected with the other elements and when certain parameters are varied, it becomes a much more volumetric and albeit a much more kind of visually complex system. And also brings up the nature of now starting to deal with the morphology of the overall system. So kind of at the meta level of not just what each element does and how one element connects with the other, but how you can vary that connection and how you can arrange the overall morphology to, in this case, actually get double curvature within each individual element, within each individual panel, but then also get double curvature on the overall form. So the overall form actually has sort of, it is quite hard to read with this translucent material, has a kind of dome-like shape to it. So we have double curvature really on all levels of the system. And then even as a kind of feedback that's a little bit hard to see here, the actual webbing of the mesh, you can see how in how the webbing is skewed. That actually gives you a description of how the forces are traveling through it. So if it's stretched in one direction more than another, then you see the change in the grid and the material, and that gives you some feedback as to how equalized the forces are in your resulting system. Of course, a regular grid is ultimately what you want, but at least the material gives us that kind of feedback. So last thing, I think the kind of ultimate question is, at least for our work, is this sort of thing, like how actually through this process, which of course combines kind of deterministic conditions as well as indeterministic conditions, how can we actually discover, possibly new principles and applications? The work thus far has been concentration most prominently on the level of geometry, because this is, with tension-active systems, an extremely challenging thing to actually master. So that's really admittedly been the first kind of concentration. How can we understand the geometry? What are the rules of the geometry? And then how can we actually start to discover possibly new geometries or new kind of larger arrangements for these structures? But ultimately we want to start to find additional performance in these kind of multi-layered volumetric membranes, whether it has to do with thermal properties, acoustic properties, how you deal with different materials at the architectural scale, all these kinds of things. So now the framework, the mindset is how, through this process, how this development and execution of knowledge in a behavior-based process, how can that start to deal with an even broader picture of performance beyond what has just been mainly geometry. And hopefully that all made some sort of sense, and thank you very much.
Questions? How would this structure perform in terms of figure-ground relations, and they are almost exclusively functional? What I have an assumption when you show that model which turns back on itself. Actually this inside structure supposed to give it some words like a form word for the tension, for the tensor. This was is it how do you stiffen, how do you get compressed elements? Is it by introducing the rods to create some kind of target exactly and tensors and this surface tensile units or some other system, because it's always I get similar things in my research, and this compression issue is something that for me and it's not you're not mentioning.
Yeah, sure. I mean, but I think it's also there's a few things. For one, it's definitely something that's considered, and in fact, this project here, though the struts are clear, so you can't see them, but you can sort of see it in that one there. At every intersection, there is a strut in there because it's very difficult across these systems to get enough tension that it doesn't flatten itself. So we certainly look at compression in terms of the system to be able to accomplish a global geometry. The next step, of course, is how you deal with the boundaries of the system, because of course you need some kind of compression element to hold it down, to suspend it within. But at the same time, and you know, this I've showed projects all the way back from my master's work, which was almost 4 years ago now, to now, and it's taken that time in terms of research to be able to get to this level of complexity in the system as tension-only systems. So what I would say, which doesn't necessarily give you an answer, but to now consider compression, it needs that same level of consideration. Recognize the other kinds of performance conditions that have to be met. So it's that would be my kind of answer to the question, that it's not that you can then say, well, okay, you have this as kind of a base, and now let's bring in a brief and let's make it work. I don't think that's really the point to it. I think the other point also is, again, through an avenue which is based upon research, it's also that the opportunities are discovered at the same time as well, and also, again, at the same time realizing the limitations too, which then the idea is that's sort of an inflection back into the brief than it is actually the brief being an imposition into the system. Yeah.
I want to ask about the difference between the first deep surface model you showed, two saddles, and all the material studies. Like the material studies have these cells connected only in points, and the first model had continuous surface.
I mean, it's maybe not apparent in this one. You can kind of see it there. There's the cable running right underneath the thank you. So, I mean, the cables are the quote unquote cables. They are built into the topology as elements which act differently to the springs, the elements which are defined to be surface geometries. It's just not so obvious as it was in that first one. But essentially all of these have some kind of integrated tension mesh system which help to distribute the forces.
But did you try to, because now these cells are connected and they distribute this force just on 8 points. Like every cell has 8 points which are connected to the other cells.
Yeah.
And if you student, it will be one continuous surface.
That is what this one does.
Sometimes
this one, you can see it not on this surface, but on the internal layer. That actually is there's a completely continuous surface which runs through this, and the only holes in the system are the ones that are defined by each cell, the cylinder of each cell. So it's in that case a combination of both continuous surface as well as sort of point-loaded surfaces, I guess, if you want to call it that, or point-loaded conditions. Sorry. Okay, thank you.